All right, guys, first thing we're going to talk about is our exponent rules, okay? I touched upon this very briefly yesterday. You guys need to know these exponent rules in and out, okay? When you are multiplying bases that are the same, when I say this, okay, if I have 6 squared, what is the base? What number is the base here? The base is the big number, right? This is our base here. The base is the big number, and 2 is our exponent. It's that little number up in the corner, okay? So when you are multiplying, a lot of times when we look at these properties and they use letters, it's kind of hard to understand. So let's think of it like this. Say I'm multiplying, I have 6 to the second power times 6 to the fourth power. Do you guys see how both of these bases are the same? It's the same number. When you have two bases that are the same and you're multiplying them, we add the exponents. So 6 squared times 6 to the fourth is the same as saying 6 to the 2 plus 4 is 6. Do you see how they did this example here with numbers? The base is the big number. When the big number is the same and you're multiplying, we add the exponents. So conversely, what's the opposite, guys, of multiplication? Division, right? Well, if you're multiplying bases that are the same, you add the exponents. The opposite of multiplication is division, yes? So what's the opposite of addition? Subtraction. So if we're dividing bases that are the same, we subtract. You subtract from top to bottom. So my base would remain the same, x, and then I say 7 minus 4 is x to the third. You guys can also look at it this way. Sometimes this can get a little confusing, like if I have 2 here and to the fifth, right? If I were going to subtract from top to bottom, this would give me x to the what? Negative 3. Very good. When we have negative exponents, I don't know if we remember this or if we ever taught this, but negative exponents, another way I could rewrite this is 1 over x to the third. If you have a negative exponent, you move it to the denominator to make it positive. If it's in the denominator and it's negative, you move it to the numerator to make it positive. Once you go through that fraction bar, it changes the sign of your exponent. Another way you guys can look at this, if I have 2 x's on top and 5 on the bottom, right? When we divide, anything on top and bottom that's exactly the same, you can cross out. So that would cross out, that would cross out. Do you guys notice how I'm left with 3 x's, and where are they? On the bottom, in the denominator. So when you have same bases and you're multiplying them, you add the exponents. Same bases and you're dividing, we're going to subtract. You guys see that? I got ahead of myself a little bit. I didn't look at the next example, but it's what we just talked about right here. But do you notice here I have y to the negative fourth. This is really y over 1. So in order to make a negative exponent positive, if it's in the numerator, you move it down. This just becomes y to the 1/4 with the y in the denominator. Okay, you guys all right? All right, anything raised to the 0 power is what number? 1. Anything. If I have 2,527 to the 0 power, what does that equal? 1. Anything raised to the 0 power is 1. Look at this. I have an entire binomial expression, x squared plus 1, but it's raised to what power? The 0 power, so that's going to equal 1. Be careful of that. You're going to have an exponent. I mean, you're going to have a question like that on your quiz. It's going to be this huge, long integer with all these exponents and stuff like that, and it's going to be raised to the 0 power. Don't get confused with that. Now, how is this different from this? How are those two expressions different? What do you notice? Okay, the parentheses. Those parentheses make a huge, huge difference. Right now, the one in red says 5 times x to the third power. The one above it, can I erase this? The one above it says 5x raised to the third power. When you have an exponent outside of the parenthesis, that needs to be distributed to both pieces. If there's 12 things inside the parenthesis, then it goes to every single one of them. So this is really the same as 5 to the third times x to the third. What does 5 to the third power mean? What does it mean if something's raised to the third power?
5 times 5 times 5.
Perfect. 5 times 5 times 5, which is 125. So this would be your simplified answer of 125x cubed is how we say that. You guys are not going to be using calculators, so it is really important that you are able to multiply. If you don't know what 5 times 5 times 5 is, then you're going to have to write it down on paper and you're going to have to work it out. All right, another thing we need to be familiar with is that you have an exponent inside a parenthesis and you have one on the outside. Well, this is called a power raised to a power. We multiply. When bases are the same, you add. When bases are the same, when you're multiplying, I should say, you add. When bases are the same and you're dividing, you subtract. When you have a power raised to a power, we multiply. So that's where we get this y to the negative 12th. And we don't like to leave exponents negative, so in order to make it positive, we'll just move it down. And we're going to do a bunch of examples to go over this. Look at this one. I have 2 over x to the third power. Do you notice where the exponent is? It's outside the parentheses, correct? That means we distribute that exponent to everything inside the parentheses. So it's 2 to the third over x to the third. Anything we can simplify, we do. So 2 to the third power is the same as 8. Okay, you guys all right? Now, I did a lot of talking here. Let's go through. I'd like to do some examples to kind of put this into action. Look at A. First of all, this is Mrs. Heron, Ms. Glick's handwriting. Anything that looks really neat and organized, it's hers. It's not mine. Okay, so what are we doing with these two parentheses? When you have two parentheses that are just stuck together, what are they doing? Multiplying. Good. So do you guys see I have a number and a number? Can I multiply those two numbers together? Yes. What's negative 3 times 4? Negative 12. Great. Now do you notice you have an A and an A? Yes? And we're multiplying them, right? So it's A to the what power? I don't see an exponent. Okay, the result is A to the second. I like it because this is A to the first and this is A to the first. If you don't see an exponent, we assume it's the 1. I like that you guys said second because what did you do to those two numbers? You added them. Good. So A squared. And then what are my B's? What's 4 plus negative 3? Positive 1. You can just leave it as B or you can put a 1 on it. That's fine. And this would be your simplified answer. Good job, guys. Bye. All right, let's look at B. Where's B? Okay, what's going on in this situation? I don't have two things that I'm multiplying together. I have a parenthesis that has an exponent outside of it. So what does that little 3 need to be distributed to? Everything. If I were you, I would draw little arrows just so you don't, God bless you, make a mistake. So I would rewrite this as 2 to the third, x to the third, y to the what? Ooh, why are we saying 6? Good, you multiply. Power to a power, you multiply. And then what's one piece now that we can simplify? 2 cubed. 2 times 2 is 4 times 2 is 8. So I have 8x cubed, y to the 6. Good job. Very good. All right, let's go on up to C. All right, I have multiplication, right? If we use PEMDAS, please excuse my dear Aunt Sally. We need to do our exponents first, right? Anybody notice anything?
It's to the 0.
What's to the 0 power? Your parenthesis, right? Very good, Faith. So look, if I distributed the 0 here and the 0 here, anything raised to the 0 power is 1. This whole expression, guys, is equal to what? 1. If I multiply 3a times 1, what's my answer? 3a. Guys, don't be fooled by that. There will probably be a question on your quiz that has a gajillion things inside of a parenthesis, and it's raised to the 0 power. Cross it out and put a 1, okay? Oh, geez. Now we got fractions and all sorts of stuff. What's the first thing I notice? There's a parenthesis with a what? An exponent where? On the outside. That means this bad boy needs to go to the 5. We got to go to the x. We got to go to the y. So rewrite it. So you distribute it to everything. 5 squared. X to the 6th. Perfect. Y to the 2nd. And there's only one little thing we can simplify, and it's 5 squared is 25, good. X to the 6th, Y to the 2nd. Very good. Questions? When we talk about radicals, guys, right, you can take the square root, you can take the cube root, you can take the 4th root, you can take the 5th root, you can take the 6th root. All that means is if you take the square root, what number of times? Oh my God. What number times itself, I have to re-listen to this video. What number times itself gives you that number? The cube root is what number times itself? 3 times. What you really need to understand is you cannot, let's write this down, cannot take the square root, the 4th root, the 6th root, etc., of a negative number. What do you notice about 2, 4, 6, 8 to even? Right? If I said to you, what is the square root of 4? You would tell me 2. If I said, what's the square root of negative 4? You would tell me, anybody? It's 2i. It's imaginary. You can't take the square root of a negative number. You can't take the 4th root. You cannot take the even root of a negative number and get a real answer. But you can take an odd root. Like, what is the 3rd root, the cube root of negative 8? Well, what number times itself gives you negative 8? Times itself 3 times? Negative 2. What's the cube root of negative 1? What number times itself 3 times gives you negative 1? Negative 1. So you cannot take the even root of a negative number. That's what I need you to remember from there. We'll talk about perfect squares. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16, and so on. It would be really helpful if you guys knew all the way up to maybe 20, but if you don't, no big deal. Again, these are the same kind of rules that we just went over, but we're going to talk here about how to evaluate, right? If you had a problem like this, it says the cube root of 8 squared. What I would tell you to do is work inside out. I'd evaluate from the inside and work out. What is 8 squared? 64. So then you figure out what number times itself 3 times gives you 64. If you notice here, you're multiplying. A house times a house just gives you a bigger what? House. If stuff is inside, it can be combined. If it's outside, it can be combined. But you cannot bring something from the outside and put it on the inside. And again, we'll talk about this more in a second. Do you guys see here on this one? You're taking the 4th root on top and the 4th root on the bottom. You can rewrite it so it's all under the same radical. How in the world did they go from this to the 6th root? How did that happen? Okay, there's 2 roots. What is the index? What's the number right here if you don't see it? 2. Very good. It's a 2 because that's the square root. So 3 times 2 gave us 6. Does anybody know the rule about when you square a square root? What happens to it? It cancels itself out. It's like those are opposites of each other. So if you square a square root, it just cancels out. So let's apply some of these properties. Square root of 8 and the square root of 2. Are they both inside of a house? Yeah. They are. So I can rewrite it as the square root of 8 times 2. And when I do that, what is 8 times 2? Do we know what the square root of 16 is? There you go. Good. Very good. What do you notice about B? You can just get rid of it. This is the index. The index is 3, and the exponent is 3. If they are the same, they cancel each other out. Your answer is 5. Good. What about here? Oh, geez, we didn't talk about letters. Same exact thing. Rules stay the same. The index and the exponent are the same. Cross them out. Your answer is X. Good. Questions, anybody? What about D? Same thing. Do you guys want a bunch of these on your quiz? Yeah, probably not, but wishful thinking, wishful thinking. But understand the property, the rule. Does that make sense? All right, good. All right, now we're still simplifying, but we have to understand what this question is asking us. It says what? Does that say the square root of 24? Does that say the square root of 24? No, it says the what? Cube root. Okay, so what does that mean? If it says what is the cube root, what are they asking? What's the question asking? What number times it? What number times itself 3 times gives you 24? So let's think about it. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. Is anything going to work? No. So, but I still think we can simplify this somehow. Can I break 24 down into different things? What are the different factors of 24? 1 and 24, right? 2 and 12, 3 and 8, 4 and 6, okay? Are any of these factors perfect cubes? Is there any one of these that you can multiply a number by itself 3 times and you get that number? 8. Very good. This one right here. So could I break this down into the cube root of 8 times 3? These first 2 lessons are just about thinking. Can I do that? What is the cube root of 8? It's 2. You can multiply 2 by itself 3 times, so you can bring that outside. Do I know the cube root of 3? Is there a number I can multiply by itself 3 times that gives me 3? No. So that's just going to stay just like that. Now remember, this exponent is 1, so it's not that they cancel each other out. So this would be your answer. We're just thinking. We're manipulating numbers and thinking about how we can break stuff down. Where's the other? Oh, there it is. All right, 4th root of 48. What number times itself 4 times gives us 48? There isn't one. So let's write the factors out. 1, 48, 2n, 24, 3n, 16, 4 and 12, 6 and 8. All right, we're talking about 4th root. A number times itself 4 times. That gives me one of these numbers. Good, very good. What number times itself 4 times gives me 16? 2. I know what you're thinking. So I can rewrite this as 16 times 3. You guys just told me the 4th root of 16. A number that times itself 4 times gives me 16 is 2. And then I'm left with the 4th root of 3. Well, I don't know what that is, so I'm just going to leave it as the 4th root of 3. All right, we're moving along. We're doing the exact same thing here, but now we're just throwing some numbers in it. What is the number right here? What is this index if I don't see one? 2. All right, so this is square root. We don't know what the square root of 75 is, but can we break 75 down? Yeah. What times what is 75? Think money. Think quarters. 25 times 3, okay. And I'm just going to write out 3 x's because that's what x to the 3rd power means. It means I have 3 of them. Square root, guys. What is the square root of 25? Okay, that can come out. Do you know the square root of 3? No, so that's going to stay inside, right? Now, squaring variables. What that means is if you have a perfect square of a variable, you're pulling out however many the index is. So every set of 2's of x's that I have, I can pull out. I have one full set of 2's, right? I mean, of x's, correct? How many pairs am I pulling out? There's 1 pair, so that comes out here. And then what's left over? An x on the inside. You cannot do anything else. If it was the square root of x to the 5th, what I would tell you guys to do is write out 5 x's. I can 1 pair, 2 pairs. How many pairs can I pull out? So it would be 2 pairs, and then I'd have the 1 left over. If it was the cube root, you'd have to pull out a set of 3. If it was the 12th root, you'd have to pull out a set of 12. A lot of times with this stuff, it's easier to just write it out so you can see it. All right, we've already had this question. I have a number and I have a letter, but I'm looking for the cube root. So what was 24, the cube root pair that we used? What times what is 24 that has a cube root in it? 8 and 3, right? So 8 times 3. And then how many A's do I have? 1, 2, 3, 4. So I know that the cube root of 8 is 2, because 2 times 2 times 2 is 8. I don't know what the cube root of 3 is, so that's going to stay inside. Cube root of 3. And then I can pull, how many A's do I need to have in a set before I can pull it out? I have to have 3. So how many sets of 3 can I pull out? 1 set. Great, guys. Very good. And that's what we're left over. Awesome. Moving along very well. Good job. Ooh, Miss Glick, Miss Heron's getting tricky. Anybody? I hear 5x because, right? This is the fourth root of the entire thing squared, or to the fourth. Do you see how the parenthesis says that the 4 exponent goes with the 5 and with the x? That's why we can do that. Good job. She's trying to be tricky. That's the only thing on that slide. Okay, now we come to something like this. Now, if I said to you, here's the problem. It's 2x minus 3y. And I said, simplify that. Can you combine those two? Why not? They don't have the same variables, all right? I'm going to say they don't have the same last name. So when you have a problem like this, you want to try to create these numbers to have the same last name. So let's see what we can do here. I have 2. What can I break up 48 into? Okay, we talked about 48 already. We did 1, 48, 2 and 12, 3 and 16, 4, oh yeah, my bad. I know I'm not using it, that's why I'm 4 and 12, and 6 and 8, right? Now let's talk about 27. 27 is 1 and 27, and 3 and 9, right? So we want to somehow break these down to a perfect square and a non-perfect square, and to where they'll have the same quote-unquote last name or same variable. Do you guys notice anything that is the same in those two sets of numbers? I see a 3 here and a 16, and I see a 3 here and a 9, right? Well, with those 3's, what do you notice about 16 and 9? They're both perfect squares. So the best way to simplify these when you get to them, I would write out like I'm doing the factors, and you'll be able to see. Some of you will be able to look at it and just do it in your head, and that's fine, but some of you will need to write it out to be able to see, and that's perfectly fine. So when I do this, I'm going to break this down. That 2's on the outside. I'm going to break this down to 16 times 3, and then I have minus, 3 stays on the outside, and this is going to be 9 times 3. So take the perfect squares out. What is the square root of 16? It's 4, right? And then we multiply these numbers on the outside. So 4 times 2 is 8. So I have 8 square root of 3. So now I come over here. Minus, what is the square root of 9? 3. Then I multiply these two numbers. So 3 times 3 is? What do you guys notice now about what we just did? Do these have the same quote-unquote last name? Like the same, you know, if they're both x's, both y's, they both have the same square root attached to them. So now can you combine them? Yes. What's 8 minus 9? What kind of 1? Negative 1. You don't have to put the 1. You can just put a negative, but we just combine those two. Some of you, you're looking at this and you're like, oh, this is so easy. Some of you are like, how do they keep breaking it down? That's okay. You just gotta think. You gotta write numbers down, write letters down, whatever you need to do to break stuff down. But you will see, or start to see a repeating pattern because there's only so many perfect squares and stuff like that. This one here is asking for perfect what? Cubes, right? So let's talk about 16. 16 is 1 and 16, 2 and 8, 4 and 4, right? Which one of those has a perfect cube? 8. So chances are really high that you're going to break this down into 8 times 2 times x, right? Well, let's talk about 54. It's a little bigger, but 1 times 54. 2 times 27. Anybody know anything about 27? What's 3 times 3? Times 3. 27. Is 27 a perfect cube? Does it have 2 in it as well? There you go. You just wrote it down. So I have cube root of, we'll say 27 times 2, and then I have 4 x's. So let's simplify each radical, and then we'll see if we can combine them at all. The cube root of 8 is 2. Can I take anything else out? No. So I'm left with 2 cube root 2x minus. What's the cube root of 27? What times what gives me 27? 3, right? 3 times 3 is 9 times 3 is 27. And then can I take anything out here? Could I take a pair out? Or a set, I should say. Right? So I can say 3x and then the cube root of 2x. Do you notice now, guys, that we have created like radicals? Yes? That's what you're trying to do here. I can't combine any more because 2 doesn't have an x. If it had 2x minus 3x, you could. But you have simplified this because you've created like radicals and you've combined as much as you could. All right, we talk about rationalizing. We're starting to use big words and it's not really that big of a deal, I promise. But when you talk about rationalizing, you cannot have a square root in a denominator. Not allowed. So when you rationalize a denominator, you get that square root out. Because what happens, if I say square root of 2 times the square root of 2, what happens? What's the square root of 2 times the square root of 2? Square root of 4, right? Which is 2. When you multiply a radical times itself, all it does is just erase the radical. So if I had something like the square root of 3 minus the square root of 2, and I said to you guys to multiply by the conjugate, you guys are like, what are you talking about? Conjugate just means I would multiply this by this. What did I change? The sign in the middle. That's all the conjugate means. If you have two terms, the conjugate, when you multiply by the conjugate, just change the sign in the middle. And when you do that, you'll end up creating a difference of perfect squares, if you will, or whatever. Meaning, what is the square root of 3 times the square root of 3?
3.
Positive 3. Perfect. What is the square root of 3 times the square root of 2? The square root of 6. Perfect. What's negative square root of 2 times square root of 3? Minus square root of 6, right? And then what's negative square root of 2 times positive square root of 2? Negative 2. So when you combine this, guys, what happens with a positive square root of 6 and a negative square root of 6? It cancels out. So what's 3 minus 2? 1. When you multiply by the conjugate, what you're going to do is get rid of the radicals. That's why you do it. And if there's a radical in the denominator, you would just multiply by that. And we're going to do some of those right now. So it says rationalize the denominator. What that's saying is, ooh, you can't have a square root in the denominator, so get it out. So what would you multiply? You don't have to do the number out in front, but you would just multiply by the square root of 3 here. What you do to the bottom, you have to do where? To the top. So when I multiply the top, 5 is on the outside of a radical, 3 is on the inside. Can I multiply them together and get 15? No, this is just 5 on the outside times 3 on the inside. That's how that works out. Then on the bottom here, because you cannot have a radical in the denominator, what you have your 2. And then what happens when you multiply the square root of 3 times the square root of 3? The radical goes away. It's just times 3. And then you can simplify a little more. You're left with 5 root 3 over 6. Question. Can I say, oh, this is a 2 and this goes away? Why not? I agree with you. You can't, but why not? Yep, because one's inside of a radical and one is not. Good. If they both are on the outside, absolutely. But since they're not, you can't do that. Good. Very good, guys. All right. Multiply by the conjugate. Just work on, let's not even look at the 2. What would be the conjugate? Don't even look at this. What would be the conjugate of negative 5, square root of negative 5 minus the square root of 7? Perfect. Square root of 5 plus the square root of 7. Perfect. So when we FOIL, square root of 5 times square root of 5 is 5. Square root of 5 times the square root of 7 is plus. 5 times 7 is 30, square root of 35. Then I have minus the square root of 35. And then negative square root of 7, positive square root of 7 just gives me minus 7. What happens with my square root of 35s in the middle? They cancel. And then what's 5 minus 7? Negative 2. Good. All right, we're just working on moving stuff around, rationalizing it, changing the denominators into something. You cannot have a radical in the denominator. Let's go here. I'm going to do some problems here. You're like, whoa, where did these fractions come from? All right, if I said to you 16 to the 1/2, that doesn't mean 16 divided by 2. This bottom number in a fraction is actually the index, the little number on your square root. So 16 to the 1/2 is just saying the square root of 16. You guys see that? So if I said 81 to the 3/4 power. 81 to the 3/4 power. How could I rewrite that as a radical from what I just showed you? What does this little number become? The 4th root, good, of 81, and it's to the 3rd power. Now, you can do these one of two ways. You can work from the inside out, like I told you at the beginning, or you can work from the outside in. You'll get the same answer. In this sense, instead of multiplying 81 times itself 3 times and then finding the 4th root, I would do this first. What is the 4th root of 81? What number times itself 4 times will give you 81? 3 times 3 is 9, times 3 is 27, times 3 is 81. So this right here that I circled is the same as 3. And then raised to the 3rd power gives me 27. You can work inside out or you can work outside in. So when we look at this, first thing I see is a negative exponent. How do I rewrite this so the exponent becomes positive? You bring it down, right? So this would be 1 over negative 32 to the 4/5 power. So now you're like, what? Okay, well, we don't like to think in fractions. I know that. So let's rewrite this. I'm going to write this as a radical. So this 5 becomes the index, right? So I can write this as 1 over the 5th root of negative 32 to the 4th power. Now, you could do this one of two ways. You can multiply negative 32 times itself 4 times and then find the 5th root of that, or you can find the 5th root first. Can you find the odd root of a negative number? Yes. So I'm going to do that. I'm going to find out what number times itself 5 times gives me negative 32. What is it? Yep. What kind of 2? So it's negative 2, and then this is to the 4th power. We're almost done. What's negative 2 times negative 2? 4 times negative 2? Negative 8 times negative 2? Positive 16. And there's your answer. So it's hard to believe that starting off with this is the same thing as that. You guys are doing a great job. We're almost done. You're doing awesome. All right, let's look at B. Ay, ay, ay. Miss Heron Glick, what are you doing here? This is combining everything we've just done. What are we doing to these 2 parentheses? We're multiplying them, okay? So let's focus first on just the numbers. Negative 5 times 3 is what? Negative 15. Agreed. So I have negative 15. Then I have an x here and an x here. And we're multiplying these two together, correct? Okay, so if you're multiplying, what do you do to the exponents? You add them. Well, isn't this peachy? 5/3 plus a negative 3/4. Okay, so we have a fraction, so that means we just stop, right? We just take our ball and go home. We start crying, I don't want to do it, I can't do it, it's a fraction. Yes, you can. I promise you guys you can. We're going to get better at this because we're going to keep doing it. What is a common denominator between 3 and 4? 12. Perfect. So you don't have to do everything in your head. Set it up just like I am so you can see what's going on. What times 4 gives me 12?
3.
If I multiply 3 on the bottom, then I have to multiply where? 3 on the top. So 3 times negative 3 is negative 9, right? Okay, this is going. So how did I get from 3 to 12? Times 4. What you do to the bottom, you do to the top. 5 times 4 is 20. Yeah? Okay. Boop, 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 boop. So now I have 20 minus 9 is what? You were going to say it right the first time.
11 over 12.
Yep, perfect. So this is 11 over 12. Now, if you're direct, you can't take the 11, 12, you can't raise x to the 11, 12. But if you wanted to rewrite it, if it said you can't have rational exponents, you can't have fractions as exponents, how could I rewrite x to the 11 twelfths?
12th root.
The 12th root of what? X to the 11th. Awesome. Negative 15. And then you'd have the 12th root of x to the 11th. Fantastic. Good. If there's no directions, either way is fine. If it says no rational exponents, then you want it like this. Rational exponents means fractions. If they want it in radical form, this is rational, and this is radical. Good question. Yeah, whatever the directions say to do is what y'all need to do. What's the last one? Oh, geez, this is easy peasy lemon squeezy. That's a 9. That's a 9. So let's first write this with rational exponents. Rational means they don't want it as a radical, they want it as a fraction. So what does this 9 do? Comes here, right? Becomes your denominator. You guys agree? Okay, so I can rewrite this as a to the 3/9. Is that simplified? No, I could write it as a to the what? To the 1 over 3? 1/3. You're fine. I know what you're thinking. You're okay. But perfect. If it's a radical, the little number, the index, becomes the denominator of the exponent. If it's a rational, then the denominator goes out front and becomes the little index. So like this one. How can I simplify this? What is this? The what root? What number goes right here? Where'd you get 6?
Multiply.
You multiply it, right? Remember, a power to a power we multiply, a root to a root we're going to multiply. So this is really the 6th root of 125. Okay, but I want this written with a rational exponent. That means a fraction. Did you say 1 over 6? Perfect. Where'd you get that 1 from? Well, the index is the 6. But you're right with that 1. Where'd you get it from, though? Is it right here?
Yeah.
But I know what you're trying. You're like, I know what I'm saying. If you don't see an exponent, you assume it's to the first power. So what we did was we said, oh, this is to the first power. Remember, your index becomes the denominator, and there you go. Good.